A library can point to the shelf where a fact lives. A human can remember a face while forgetting the name. But ask an artificial intelligence for the capital of France, and where exactly does Paris come from? Is there a Paris drawer somewhere inside? Does the machine have concepts? And when it explains an answer, are we watching its reasoning or only hearing a convincing story about it? The simplest picture is a filing cabinet. One fact, one file. Real language models do not work that way. Words are turned into patterns of numbers, and each new word changes activity across many layers. Some parts matter more than others. But a familiar answer usually emerges from a shifting pattern, shaped by the question around it. Paris in a travel plan is not quite Paris in a history lesson. Knowledge looks less like a stored sentence, and more like a route that the model can rebuild when needed. That creates a problem for anyone trying to look inside. Imagine a sound engineer with thousands of meters, each reacting to several instruments at once. One meter might rise for the piano, a singer, and the hiss of a cymbal. In a model, a single artificial neuron can also respond to several apparently unrelated things. Reading one neuron at a time can be like trying to identify an orchestra from one flickering needle. Researchers are building better instruments. One is called a sparse autoencoder. In plain language, it tries to separate a crowded signal into a smaller set of features that make sense more often. Perhaps references to a famous person, a programming error, or an idiom. OpenAI reported 16 million such features from one point inside GPT-4. Google DeepMind released hundreds of similar tools for Gemma, containing more than 30 million learned features in total. Those numbers sound like a map. They are not. Many features are unclear, some overlap, and the measuring tool itself loses information. These are candidate landmarks, not labeled boxes inside a brain. Still, some landmarks are surprisingly recognizable. Anthropic tested the same simple ideas in English, French, and Chinese. In selected examples, Claude used overlapping internal features for meanings such as small, large, and opposite, even though the words were different. That suggests at least some concepts are shared across languages inside the model. It does not prove a universal language of thought. But it is more than noticing that the final sentences look alike. Researchers measured the activity in between. Other experiments follow a fact as it is assembled. Ask for the capital of the state containing Dallas. In one traced example, the model first activated Dallas, then Texas, then Austin. That sounds obvious to us. The important part is that the route appeared inside the computation, before the answer reached the screen. Then, the researchers did something stronger than observation. They altered the internal state representing Texas, pushing it toward California. The answer changed from Austin to Sacramento. This is a causal test. Change one suspected link and see whether the result changes in the predicted direction. It is closer to switching a wire in a working machine than taking a photograph of the control panel. But even here, the tracing system is an imperfect stand-in for the original model, and the map captures only part of what happened. The same approach can reveal planning. In one poetry task, internal activity pointed toward a future rhyme before the model had written the line leading to it. Suppress that planned word, and the poem bends toward a different ending. Yet another finding is less comfortable. A model can print a neat chain of reasoning that does not match the mechanism researchers detect inside. The written explanation may be useful, but it is not automatically a transcript of the hidden computation. That matters whenever we ask an AI to show its work. Then comes a stranger clue. In Anthropic's subliminal learning experiment, a teacher model was given a preference for owls. It generated long sequences of numbers. The researchers filtered those sequences so they contained no obvious owl references. A student model, built from the same base model, was trained on the numbers alone. Before training, it chose an owl about 12% of the time. Afterwards, more than 60%. A preference had crossed through data that looked unrelated to the preference. That does not mean the models invented a secret owl language. The effect depended strongly on teacher and student sharing the same underlying model. With different base models, it generally did not transfer. The careful conclusion is narrower and perhaps more useful. Model-generated data can carry model-specific statistical signals that human reading and ordinary meaning filters may miss. Researchers can measure the behavioral effect. What those signals represent and how broadly they matter remains unsettled. So how much of the black box is open? Not enough to declare victory. Anthropic reported satisfying circuit tracing insight for roughly 1/4 of the prompts it tried. Its replacement system reproduced the original output in about half of tested cases. Long prompts remain difficult. Some important activity is missing from the diagrams. And independent researchers argue that sparse autoencoders may divide the same activity in several valid ways, rather than discovering one final set of atomic concepts. We may be surveying real streets while still disagreeing about the best map. But something important has changed. Researchers are no longer limited to asking a model a question and judging the reply. They can record internal activity, propose a mechanism, intervene, and test whether behavior moves as predicted. These tools may help diagnose failures, monitor dangerous tendencies, and compare what a model says with what appears to drive it. They can also fail, simplify, or tempt us into seeing a clean story, where the machinery is messier. Interpretability is becoming an experimental science, complete with instruments, arguments, and error bars. Where does an AI keep what it knows? Today, the honest answer is across measurable patterns and pathways that we can sometimes identify, test, and change, but cannot yet fully describe. The machine is not an empty trick simply because its workings are hard to see. Nor is every colorful feature map a window into a mind. We are learning to illuminate a few routes through an enormous city. The lights are real. So are the districts that remain dark.